Welcome to AI Paper Slop. If you are writing the training loops for an embodied AI right now, you are probably agonizing over your compute budget, just wondering why throwing more GPUs at your vision language action model isn't actually yielding better manipulation.
Right. It's incredibly frustrating.
Yeah, and today we are jumping straight into the answer. The paper is called Affordance-VLA, a vision language action model empowering action generation through Affordance-Aware understanding. It was published April 10th, 2026 by Quizu and a huge collaborative team out of Peking University, HQS, and a few others.
And to give you the core insight right away, the authors basically prove that blindly scaling training data for these vision language action models, or VLAs, has hit a brick wall.
Literally a wall.
Exactly. And it's because of this spatial gap between a VLM's 2D semantic understanding and a robot's actual 3D physical control.
So their solution to this is AffordanceVLA. They introduced the structured affordance forecasting intermediate layer broken into which to act, where to act, and how to act.
Right, which they house inside this really interesting mixture of transformer architecture.
Yeah, and the result is wild. By converting every single training sample into a dense signal for object grounding, spatial localization, and 3D geometry, AffordanceVLA just totally shatters the sample efficiency ceiling.
It really does. I mean, it hits higher performance on benchmarks like Libero, with just 40% of the fine-tuning data that a massive model like PO needs.
Which is just, 40% is crazy.
It's a paradigm shift, honestly. For engineers who are just tired of brute-forcing model scale, this proves that representation is the real bottleneck, not just dataset size.
Okay, let's unpack this a bit. Because to understand why AffordanceVLA is such a big deal, we have to look at why end-to-end mapping was failing so hard.
Yeah, the old default industry move.
Right. You take a massive pre-trained VLM, which is, amazing at aligning vision and language in a semantic space, and you just try to force it to spit out robotic actions directly.
But the issue there is that pre-trained VLMs, they live entirely in a world of semantic concepts.
They know what the word mug means.
Exactly. It knows a coffee mug holds liquid, and it knows what a mug looks like in a 2D image. But embodied control is inherently 3D. It's physical.
It's geometric.
Right. The model needs to know the exact millimeters of depth, the orientation of the handle, the layout needed to close a gripper without just, smashing the cup.
And previous attempts to bridge that gap use things like video prediction, right? Like visual foresight.
Yeah, making the model hallucinate future video frames to guide the action.
But dense visual signals have so much useless information, like it's trying to calculate the rendering of sunlight on the wall behind the mug just to move its arm.
It's incredibly slow and computationally completely irrational. Predicting pixels is not the same as predicting physics.
Right. It's like, okay, imagine trying to teach someone how to physically drive a manual transmission car, right?
Okay.
But you only show them an endless stream of 2D photographs of cars driving on a highway. You never give them a physical map of the steering wheel or tell them where the clutch bite point is.
You're just flashing JPEGs at them.
Yeah, just flashing JPEGs and saying, figure out the footwork. Yeah. Are we finally admitting that the era of just add more compute is hitting a wall in robotics?
We have to. VLAs are fundamentally representation learning systems. If that intermediate translation layer is flawed, your ceiling is low no matter how big the model is.
So since scaling isn't the answer, the conversation naturally pivots to the author's structural solution.
The 3 pillars of affordance.
Yes. They decompose this messy perception to action mapping into 3 interpretable sub-problems: which to act, where to act, and how to act.
And what's fascinating here is how these cues serve as a natural bridge. They anchor VLM semantics straight into action generation.
Here's where it gets really interesting to me. Because of this decomposition, every single piece of training data now supervises grounding, localization, and geometry.
It's basically multiplying the learning signal of the data.
Exactly. Let's break those down. First, which to act. This handles object-centric grounding, right, to suppress visual distractions.
Right. And a crucial technical detail here, they actually redesigned this from a VQ-VAE to a continuous flux VAE.
Oh, wait, the discrete versus continuous thing.
Yeah. They wanted to avoid hard constraints on token counts. Discrete tokens force arbitrary boundaries, which in the physical world means your robot clips the edge of the mug.
Because reality doesn't have blocky pixel borders.
Exactly. Physical reality is continuous.
Okay, so that's which to act. Once it isolates the object, we move to where to act.
Right. Where to act handles 2D interaction localization.
By projecting a heat map onto the 2D observational plane, basically telling the robot, here is the actionable region.
But a 2D heat map doesn't give you depth.
No, it doesn't. And that's where the heavy lifter comes in, how to act, the 3D geometric reasoning.
The engineering on this pillar is intense. They use a conditional diffusion process with an iterative transformer denoiser.
To generate a 3D shape latent, right?
Yes, and then they run that through a multilayer perceptron and MLP to regress a 10-DOE spatial layout vector.
10 degrees of freedom, so that's translation, rotation, scale.
Yep, the X, Y, and Z axis, a full 3D rotation matrix, and the gripper state parameters. It's a precise mathematical mapping.
So it takes this fluffy, high-level language command like pick up the mug and locks it into strict math.
Exactly. It's spatially grounded, semantically conditioned, and action-coupled.
But wait, this brings up a huge question about the architecture. How do they actually balance learning broad vision language concepts alongside these super specific 10-DOF regressions?
That's where the mixture of transformer, or MOT architecture, comes in.
Yeah.
They decoupled the model into specialized experts.
Okay, I have to push back on this a bit. Why decouple it? We've seen monolithic transformers swallow every other domain.
True.
Like LLMs do coding, reasoning, translation, all in one massive block of weights. Why couldn't they just use a single transformer to handle everything here?
It's a fair question. But if you do that in robotics, you get representation collapse.
Really? Why?
Think about the frequencies of the data. Semantic understanding operates at a low frequency. Broad concepts. Low-level physical control data is incredibly high frequency.
Oh, right, like millisecond level precision.
Exactly. If you force a single set of weights to optimize for both, the high-frequency physical data just erodes the high-level semantic abilities. The MOT design prevents that.
So the semantic understanding stays intact in the understanding expert, while the low-level control is localized to the action expert.
Exactly. You quarantine the physics engine from the language engine.
That makes so much sense. Okay, so how do they train this beast? They use a very specific 3-stage curriculum.
Yeah, starting with stage 1, which is basically standard pre-training.
Visual question answering, basic visual language alignment.
Right, teaching the model what the world conceptually looks like. Then comes stage 2, the co-training stage, which is arguably the most critical step.
This is the large-scale simulation data, right? Intern data A1.
Yep. They expose it to affordance-centric robotic data in SIM, and skipping this stage is catastrophic.
Yeah, I saw the ablation study on this. If they skip stage 2, the out-of-distribution generalization on the Kelvin benchmark just absolutely tanks.
It drops down to a 3.81. It's abysmal. It proves you can't jump from broad internet images straight to real-world robotic fine-tuning. The simulation provides perfectly clean, dense affordance labels, like exact 3D bounding boxes.
Because real-world data has sensor noise and occlusion.
Exactly. But you can't stay in simulation forever, so stage 3 is post-training and fine-tuning.
Using real-world datasets like Droid to bridge the sim-to-real gap, and then fine-tuning on target datasets like Libero.
But there's a huge logistical hurdle here. Dense affordance labels are so expensive to get in the real world.
Right, you can't just pay human labelers to manually map millions of frames with 10-def spatial layouts. It would take forever.
So the authors built a robust automated data augmentation pipeline.
But wait, automating physical labels sounds incredibly risky. Like a slightly wrong semantic label is fine, but a slightly wrong 10-def label means the robot smashes into a table.
Exactly. Physical priors are unforgiving. That's why they instituted a 100-round random sampling human audit protocol.
100 rounds?
Yeah, and it required a 100% pass rate to clear the augmented data for training.
That is strict.
It has to be. Even a tiny percentage of poisoned spatial data will corrupt the entire action space.
Okay, so they built the architecture, they secured the data pipeline. What does this all mean for the ML engineer listening to this? Let's talk about the empirical results.
The data efficiency is where this model truly shines.
Yeah, they benchmarked it against PO, right?
Right. A fully fine-tuned PO model hits a hard performance ceiling. You can feed it terabytes of data and it just plateaus. AffordanceVLA breaks right through that ceiling.
Using only 40% of the fine-tuning data.
Exactly. With just 40% of the data, it hits around a 92% success rate on Libero.
That is wild. And on Kelvin, which is the long horizon stuff, it got an average chain length above 4.0.
Which means it can sequence multiple distinct actions in a row without dropping context.
And the ablation studies proved this isn't a fluke. The no-AFD model, the one without the affordance structures, struggled to even surpass PO.
Yeah, it recovered very slowly. It completely proves that robotic pre-training data alone just offers limited scalability.
You need the which, where, and how structures to actually extract the physical lessons from the pixels.
This raises an important question, honestly. It challenges the standard industry approach.
How so?
Because this paper proves the datasets themselves are not the bottleneck.
The representation is.
Exactly. We have to stop treating VLAs as black boxes that will just magically infer physics if we show them enough YouTube videos.
So what this all means is that architecture, representation, and data quality are mutually amplifying. You can't just substitute good architecture with massive, messy data.
Precisely. Affordance-VLA proves that injecting physical, task-oriented priors into VLAs completely alters the sample efficiency curve.
It's honestly a huge wake-up call. And it leaves me with this really provocative thought, something that wasn't explicitly in the paper but builds on it.
What's that?
Well, if introducing explicit affordance intermediates like 3D shape and 10-DUF layouts improves sample efficiency this drastically, what other implicitly learned physical priors could we structure explicitly?
That's a great question.
Like, could we build a physics VLA? One that explicitly forecasts mass or friction coefficients or material deformability before it even generates an action.
Oh, wow. Yeah, an architecture that inherently understands that a foam block and a steel block might share the exact same 3D shape, but require completely different force feedback.
Exactly. Would that unlock the next leap in generalized robotic intelligence? If layout did this much, imagine what mapping out dynamic physics properties could do.
It would completely change the game.
It really would. Well, that is something for all of you to mull over. Thank you so much for joining us for this deep dive into the research today on AI paper slop.
Yeah, thanks for listening.
If you want to stay up to date with the latest AI research and these kinds of paradigm shifts, be sure to subscribe. Catch you next time.